In this video, we're going to continue topic 4.4 and we're going to look at explain 4, which is showing us a real-world problem using complex numbers. So electrical engineers use complex numbers when analyzing electrical circuits. An electric circuit can contain three types of components: resistors, inductors, and capacitors. As shown in the table, each type of component has a different symbol in a circuit diagram, and each is represented by a different type of complex number based on the phase angle of the current passing through it. So the resistor, it gives you this little zigzag symbol, and its angle phase is 0 degrees, and it is the real number. And inductor, it gives you like the curly cues, and it is phase angle is 90 degrees, and it's an imaginary number where B is positive. So I assume it's a positive B value. And then the capacitor gives you this little set of parallel lines. Its angle phase is negative 90 degrees. And notice the B value has to be negative in this case. So in a diagram of an alternating current, AC current, electric circuit is shown along with the impedance measured in ohms. So this funny little symbol represents ohms. Each component in the circuit, an AC power source, which is shown on the left in the diagram, it's actually on the right, and labeled with 120 volts for the V for the volts, causes electrons to flow through the circuit. Impedance is a measure of the components. So impedance is a measure of each component's opposition to the electron flow. So what we're supposed to do is use the diagram of the electric circuit to answer the following questions. The total impedance in the circuit is the sum of the impedances. So total impedance is the sum of the impedances of the individual components. What is the total impedance for the circuit? Write the impedance for each component as a complex number. Well, we know that this one here is a real number, okay? So I know that's real, so that's just going to be a 4. And then I know that this number here, because that's the inductor, is a positive imaginary number. So I'm going to write that one as 3i. And then I know this one here, the capacitor, is a negative imaginary number. So I'm going to write that one as negative 5i. Now we're supposed to find the total sum of the impedances. So we're going to do what we were doing in the notes there. We are going to do 4 plus 3i minus 5i, which is going to be 4 minus 2i. In part B here, it says Ohm's law for AC electric circuits says that the voltage V measured in volts is the product of the current I measured in amps and the impedance Z measured in ohms. And then they give us a formula. So voltage equals the impedance times, the current, which is the I, times the impedance, which is the Z. For the given circuit, the current is 24 plus 12i amps. What is the voltage for each component of the circuit? So they're telling us that the current I is this 24 plus 12i. We need to go and find the voltage for each component. And remember, Z is the impedance from each part in A. So in A, we know for the resistor that our impedance was 4. So I'm going to distribute that 4 in. So when I distribute the 4 in, I get 4 times 24, which is the 96, and 4 times 12i would be 48i. For the voltage of the inductor, I'm going to multiply by the 3i, and this is going to look a little bit different. So when I do 3i times 24, I get 36i. So that's going to go in the back, actually. I do not get 36i. I get 3i times 24 is going to be 72i. Sorry about that. 72i. And then 3i times 12 is 36i squared, which is going to be better known as the negative 36. So it actually brings it up front. The voltage for the capacitor would be 24 plus 12I times the negative 5I. So I'm going to use that this time. So negative 5I. So when I multiply 24 times negative 5I, I get negative 120I. When I multiply 12I times negative 5I, I get negative 60I squared, which I better known as when I change the sign as 60. Then the final piece of this is in the reflect. Find the sum of the voltages for the three components in part B. What do we notice? So we're going to add up these three components that we found in part B. Okay. So we have 96 plus 48I minus 36 plus 72I plus 60 minus 120I. I am going to combine my like terms. So 96 minus 36 plus 60 is 120. And then we've got 48I plus 72I minus 120I actually happens to be 0I. So that goes away and I have just 120. And then it asks us, what do you notice? Well, if you take this 120 and this said it was the voltage, you come back up to our original, notice that the diagram showed us that we had 120 volts in that circuit. So I would say that the sum of the voltages equals the voltage supplied by the power source. All right, and we are going to skip number 13, so that means you are done. Please make sure you are answering your elaborate questions.